So what happens to wind as you go away from the surface of the earth? Two things happen. One, it's going to speed up because now it doesn't have the influence of the frictional force of the earth, right? Number two, and since the winds are going faster, there's something called as the Coriolis Force, which is going to deflect the winds, right? And therefore, once in the Coriolis Force in the northern hemisphere is going to deflect everything to the right, right? Therefore, where's the wind coming from? You said 300?
300.
Yeah, so whatever was coming from 300, which is somewhere here, will now get deflected to the right, which means now it will start coming from 310, 320. So winds will become more northerly and faster. Number 5. Degrees magnetic. Planned track distance is 96 nautical miles. So this is a planned track of 250 degrees magnetic here.
Magnetic.
That
Distance is
from
96 nautical miles.
96 nautical miles. Yes.
Yeah. Heading is okay. So heading is 260.
That's Norwich to Oxford. Right. That's right. So Norwich to Oxford, 250 degrees is the planned track and 96 nautical miles is the distance. So we have all this as part of your pre-flight planning. On your flight log, you have all these things entered. What is the heading? The planned heading is 260 degrees magnetic. 260. Right. So basically, this is a track of 250. So 260 heading is going to be towards the north. Right. It's like that. Exactly. So as I told you, let's hold the aircraft a bit. Let's see the track, and then we will place the aircraft after that. All right. Now, what is the ground speed?
The ground speed, it is 180 knots.
That's right. Ground speed is equal to 180 knots. Perfect. And so all these planned values, sir. The aircraft departs Norwich at
10 a.m.
hour. So what is that? This is the actual time of departure, ATD, right? So usually what we do is you take off, and once you reach midway through the runway, that's right time to actually know this actual time of departure. Or if you're actually overhead the destination, you can even consider that as the actual time of departure, because it's point to point time basically, right? So you might take some time to climb all the way and reach, but if you are overhead the runway, if you are doing an overhead departure, in that case you can take that time as well as the actual time of departure. All right. Yes. Now the aircraft departs Norwich at 10 o'clock. At 10:12 the aircraft is overhead L. Now where is L? 3 nautical miles right of planned track. Right, so you're traveling from Norwich to Oxford. So 3 nautical miles right of planned track is actually to the north of this particular track.
North of, yeah.
Right, so somewhere at some distance away from N, you are found to be 3 nautical miles off
3
track.
nautical miles. Okay.
And
time
that's
10:12.
That's right. And the time is 10:12. Now time is very, very important as far as your position fixing, situation awareness, everything is concerned. So if you lose track of time in the aircraft, it's very, very difficult to navigate. Right? So you should know what time, where would you reach at what time. That is why we keep revising our ETAs. And that's why we do 1 in 60 and stuff. So 1 in 60, as far as your theoretical syllabus is concerned, doesn't really talk about revising the ETA, except for this question. But in the actual flight, you do 2 different things at the 1 in 60 point. One is definitely you apply the 1 in 60 tracker, or you change your heading accordingly to fly to the destination or intercept and fly. Or number two is you revise your ETA. And that is what I have explained to you in the very first session of 1 in 60, where we have revised the ETA twice, if you remember, and we've also found out the 1 in 60 track. Alright, so at LE, at 10:12, you find yourself 3 nautical miles off to the right. So we imagine that you have some kind of a 1 in 60 fixed there, and you find yourself to the right of track. Alright, now what?
It says that using 1 in 60, find that. Okay.
Find the following using 1 in 60. What is the first one? Is the planned track.
The planned drift.
Oh, so the planned drift? Sorry.
So my track was 250 degrees magnetic,
So
and my heading is 260. So measured from the planned drift is the angle between the heading and the planned track.
It's heading and the planned track measured from the heading. So what's the heading?
My heading is 260 and my planned track is 250. So it is a drift of
exactly. So
10 degrees towards pole.
Exactly. So you have heading of 260, planned track is 250, which means you measured from the heading towards the track you have a port drift of how much?
10 degrees of port drift.
That's right, 10 degrees of port drift. If I don't do anything about it, I'll be drifting towards the port. Alright, yes. What is the track error at 10-12 hours? Track error at 10-12 hours. All basic questions. To find track error, along with the planned track, I also have to draw the track made good, or the actual track. So let's draw that. This is the track made good, or the actual track. Right? Now, measured from the planned track towards track made good is what is called as track error. Yes. Now what?
So in order to calculate the track error, we have the distance off, but we don't have the distance gone.
Yeah, we don't have this distance gone here. Yeah, so let's look at the equation here. So 160 track error is equal to distance off.
Distance off by distance gone.
Gone into 60. Yeah. So what do we have?
So we have the time and the ground speed. So using the time and the ground speed, we can calculate the distance gone.
That's it. So we have the distance of given the question at 3 nautical miles. You have to find out the distance gone. So what is the actual distance? Where will you actually measure this distance gone? It's measured from the point N to a line. This is the actual distance gone. But as we know that since we are looking at smaller angles, the difference is actually considered negligible. And for that reason, we can actually take this and these distances as the same. So distance off by distance gone can be taken as the same distance over here. So how will you find the distance gone? The distance speed is equal to distance by time.
Our ground speed is 180 nautical miles divided by 60 will give it per minute multiplied by 12 minutes.
So it's 180 is in nautical miles per hour. The time is in 10 hours, 10, 12. Therefore the time interval, the actual time interval ATI is 12 minutes. Right? So since this is in nautical miles per hour, I have to make this also in hour. Therefore that's going to be 36.
36 nautical miles.
Nautical miles. So what is 36 nautical miles? Actually the track made good is of length 36 nautical miles, but I can take this as 36 nautical miles as well, because it is quite negligible. This difference is not considered significant. After all, 160 is an approximation anyway. Right. So what is the track error now?
So my track error is
3 nautical miles.
Okay.
Over
3 nautical miles divided by 36 multiplied by 60.
Yeah.
It is giving me 5 degrees.
5 degrees. Yes. And
Yes, 5 degrees. So 5 degrees towards right.
Towards right. Very good. Because track made good is right of the planned track. Right. So what is the question? You asked to find the track error at 10-12. So track error at 10-12 is how much? 5 degrees right. Alright, perfect. Now, what track made good has been flown between 10 hours and 10-12 hours? So it's just a relatable, just next part of the question. You have to find the track made good.
So it's 255 degrees.
That's right. So basically planned track is 250 and now you measure clockwise 5 degrees. So it's going to be 255 degrees magnetic. So the track made good. Yes, 255 degrees magnetic. So think about 250 plus 5. Alright, D is what has the actual drift being between 10 and 10-12. We have to find out the actual drift.
So actual drift is basically the angle between the heading and the actual track or the track measured from heading.
Very good.
So my heading was 260 degrees.
Exactly.
And my track made good is 255 degrees.
Yes, we should just found out here. Right, so now we can put that heading into the picture here. So how will I draw the aircraft? 260 is here. Right? This is the heading of 260 degrees magnetic. You have to find out the actual drift. As you told rightly, it's between heading and track made good. So track made good is right here. The heading is always measured from the heading towards your track made good. What is the angle? 255 and 260. Therefore it's 5 degrees.
5 degrees left.
Left. Why is it left?
Left is port.
Yeah, but why is it port?
since like 260 is greater and 255 will be.
Yeah, so your track is towards the port of the heading. Right? Perfect. Yes. Now E. What heading is required to fly direct to Oxford? What heading is required to fly direct to Oxford? So let's, as I told you, when you're going to get question heading, always settle down with the track first before you think about the heading. So let's see what track is required to fly towards Oxford, and then you can find out what the heading is. Right? So I have to fly this particular track here.
I'll have to first make the correction for divergence.
Correct. So this is a track required to be flown, right? Yes. Now we are asked to find out the heading required. Yes. How will you find out?
Yeah. So first I'll have to stop my drift.
Yeah.
So that will be basically equal to my track error.
Exactly.
In this case, it will be 5 degrees towards the left.
Yes.
Of my heading.
All right.
Then I'll have to fly directly towards Oxford, and that is basically equal by the angle of closing angle.
Exactly. Yes. So basically, first thing first, if I don't do anything about it, I'll keep drifting on a track of 255 degrees magnetic. Right? Now, as you rightly said, to prevent the drift or to stop the divergence, I have to now fly a track that is parallel to my planned track of 250 degrees. Therefore, what is the track change required? It's simply 5 degrees to the left. Right? Now I have to track direct to the destination. I have to make further change to the left by an angle equal to the closing angle. And how will you find the closing angle here?
It is basically the angle that is equal to the distance off by distance more to go.
Distance to
distance
go.
to go multiplied by 60.
60, yes. What is distance off?
Distance off we know is 3 nautical miles.
Okay.
The total distance is 96 and already we have flown 36. So the
Exactly.
value is 60 nautical miles.
So total distance is 96. You've only flown 36 here. Therefore, this distance is 96 minus 36, which is 60 nautical miles.
60 nautical miles.
Right?
So directly also, yeah.
Perfect. So let me just put the 60 nautical miles here. All right. Yeah. Now.
So we can calculate it, so it is 3 degrees.
Yeah. So 60 nautical miles over 3 nautical miles. Nothing much to do here. I'm not doing it. So just straight here. This is 60 already. So it can't be.
3 degrees. So
Right.
it is equal to the closing angle, that's it. So
Exactly.
it is 3 degrees to the left.
Exactly. So it's going to be 5 degrees plus 3 degrees to the left. So total track change required is equal to
Is 8 degrees of left.
so track change, which is equal to your heading change, and that is equal to 8 degrees. This is 5 plus 3 to the left, right? So since track change is equal to heading change, what is the, you have to find what is the heading, what heading is required to fly direct to Oxford? What is the new heading to fly direct to Oxford? How will you find out?
Echo where, what is the alteration of heading should be made to fly directly to Oxford?
What is does
8
echo?
degrees left.
Oh, sorry. What is the alteration of heading required to fly direct to Oxford?
8
Yes.
degrees left.
That's right. The alteration of heading required is, that's right, 8 degrees
8
left.
degrees left.
Correct. All right. Now let's look at foxtrot.
Yeah. So what heading is actually required to fly directly to Oxford?
Exactly.